All right, practice problem number 1. What is the wavelength of radiation in nanometers that has a frequency of 8.79 times 10 to the 15 reciprocal seconds? And for frequency, sometimes they put cycles per second, and other times they just put 1 over seconds, which is called reciprocal seconds, because the cycle is kind of assumed. So we know that the frequency, this is nu, the Greek letter nu, is 8.79 times 10 to the 15th reciprocal seconds. That means 1 over seconds, or cycles per second. Also, we know c is the speed of light, 2.9979 times 10 to the 8th meters per second. The relationship, the speed of light in meters per second is equal to lambda, the wavelength, in meters per cycle, or just meters, times nu, the frequency, and this is in cycles per second, except again, a lot of times we don't even worry about the cycles, in which case this would be meters and this would be seconds to the -1. But you do need to be conscientious, even though it's a simple equation, you have to be conscientious of units. So if you rearrange this, of course, lambda is going to equal the speed of light over the frequency. That's what the problem's asking for. And speed of light 2.9979 times 10 to the 8th meters per second divided by the frequency 8.79 times 10 to the 15th reciprocal seconds. This is 1 over seconds, but this is 1 over seconds, so they cancel. And this wavelength will be in meters. But that's not what the problem asks for. It wants a wavelength in nanometers. And so he also, in fact, you can even put it in this calculation if you want. Just do it all in one step. Milli, micro, nano, 1 meter is equal to 10 to the 9th nanometers. And so you multiply this times 10 to the 9th nanometers over 1 meter, and the meters cancel. Okay? Everybody see how to set that one up? When the speed of light was in meters per second, the frequency was in reciprocal seconds, but the problem wants the wavelength in nanometers. So you can do this, your answer will be in meters, and then you need to convert it to nanometers. Okay? Or you can do it in one calculation. Okay? Again, none of this you have to memorize. This equation will be on the formula sheet. 1 meter is equal to 10 to the 9th nanometers. Let's move on to number 2. Number 2, calculate the frequency of visible light that has a wavelength of 686 nanometers. And again, rearranging the same equation. Frequency is going to equal the speed of light divided by the wavelength. So we have 2.9979 times 10 to the 8th meters per second, the speed of light. The wavelength, we have 686 nanometers. And then we can either convert the meters to nanometers up here, or we can convert the nanometers to meters down here. If we do it up here, let's just go ahead and use the factor we had before. 10 to the 9th nanometers over 1 meter will enable us to cancel the meters here. And then the nanometers can cancel. You gotta be conscientious of units. Or if you wanted, you can convert nanometers to meters before you even do the problem. Okay? Everybody see how we set that one up? All right, number 3 here. We mentioned that electromagnetic radiation includes visible light, radio waves, microwaves, infrared, ultraviolet, gamma rays, X-rays. It's all the same thing. Our eyes can only see a narrow range from 400 to 700 nanometer wavelength of electromagnetic radiation, but we still get to see all the beautiful colors that we see. Well, in this problem, no matter what kind of electromagnetic radiation it is, the smallest particle is called a photon, and it can be thought of as a packet of energy, if you will, in the way that it interacts with matter. It's asking what is the energy in joules of 1 photon of microwave radiation with a wavelength of 0.179 meters. So that's a pretty big wavelength. It's pretty low energy. It's not as big a wavelength as radio waves that you listen to on your radio. They may be the size of a football field. The longer the wavelength, the lower the energy of the photons. Whereas you have something like gamma radiation, the wavelength's ridiculously small. The frequency is extremely high. So, the energy of a photon, again, is a very simple equation. It's equal to Planck's constant times nu, the frequency, or it's equal to Planck's constant times the speed of light divided by the wavelength. And the problem gives you the wavelength and the speed of light and Planck's constant. So, Planck's constant is 6.626 times 10 to the minus 34 joule seconds times 2.9979 times 10 to the 8th meters per second divided by, conveniently they give you the wavelength in meters so you don't have to worry about changing it. The wavelength's 0.179 meters, and so the meters cancel, the seconds cancel, and the energy of the photon is going to be in joules. Okay? It's the only thing left. Does everybody see how we set that one up? And that one wasn't too bad because we didn't have to convert anything to anything. Now the equation for the energy level of electrons in a hydrogen atom, I think we emphasized, is misleadingly simple. It's only hydrogen that has such a simple equation. All the other elements of the periodic table, they have to use a Schrodinger wave equation to do complex calculations when you have more than 2 electrons in an atom, or 2 or more. But Bohr, the scientist Bohr, it's B-O-H-R, not boring, Bohr, came up with this very simple equation for the energy levels in hydrogen. And it's on problem number 4. Calculate the energy in joules required to excite a hydrogen atom by causing an electronic transition from n equal 1 to n equal 5. Recall that the energy levels of a hydrogen atom are given by the simple formula the energy of an electron in the nth energy level is the Rydberg constant times -1, I should say, minus 2.18 times 10 to the minus 18 joules times 1 over n squared. That's extremely simple equation. And there's more than one way to do a simple problem like this. But one way is just to figure out the energy of the electron at each energy level and subtract them. Okay? Let's think about what's going on here. If you have an electron in an orbital, and we're talking about hydrogen at the moment, and it has other orbitals with other energies. If an electron absorbs a photon of the right energy, and then has an energy exactly equal to this change, it will cause the electron to go to a higher energy level, and we call that an excited state. So if an electron's absorbing electromagnetic radiation and going to a higher level, that's one type of problem. It started here and it ended up here. On the other hand, if an electron's in an excited state to begin with, and it returns to a lower energy level, well, now it's going to give off a photon that's equal to this change in energy. So the first example, it was absorbance of a photon. The second example is it's emitting a photon. In problem number 4, the electron is absorbing a photon. It starts out at n equal 1 and it goes up to n equal 5. Well, the change in energy, which would also happen to equal the energy of the photon, by the way, that caused it, is just going to equal the energy it ended up minus the energy it started out. And so if you calculate each of these, you just subtract. So energy, and when the electron's in the 5th energy level, this is just a -2 point, and again, this has to be hydrogen. It can't be one of the other elements for such a simple equation. And of course, it's in the 5th energy level, so we have to multiply that times 1 over 5 squared, don't we? Or 1 over 25. In other words, we just take this divided by 25. Right? And then the first energy level is equal to the same -1 times the Rydberg constant here. Except it's got to be over 1 divided by 1 squared, which is the same thing as this, isn't it? This is going to be 1. 1 over 1 times this gives you this. Once you know each of these, you subtract E1 from E5 to get the answer. Does everybody see how to do that problem?
Yes.
Okay. Oh, boy. Number 5, now this is one way you can do it, and number 5 we'll look at it, it's a different problem, but there's another equation. Again, it's just based on the same one we just used, but number 5, you have the wavelength of light emitted by a hydrogen atom during a transition of the electron from n equal 5, now this time to n equal 2. So it's excited. Maybe you've got hydrogen in an electron discharge tube, you apply electric current. Some of the electrons go to the 5th energy level, and then they drop down to the 2nd one, and they emit a certain wavelength of light when they do that. Okay? Another approach, we could obviously determine the energy of electron in the fifth energy level and the energy in the second, and we can subtract, just like we did over here. Or there's another way of doing it, just it combines these two terms, this change in energy, which is the energy of the photon, this change in energy is equal to the Rydberg constant times 1 over the initial quantum number squared minus 1 over the final quantum number squared. Here you just do it in one calculation. These got flipped, so you got rid of the negative sign that you saw over here. And this Rydberg constant is the same thing as 2.18 times 10 to the minus 18. It was initially in the fifth energy level. It ended up in the second energy level. Okay? Everybody see how we got this? Now this is the energy of the photon. Well, that's the energy, but that's not what the problem's asking. Once we have the energy of the photon, what do we have to figure out?
The wavelength.
The wavelength. Well, the energy of a photon is equal to Planck's constant times the frequency, or Planck's constant times the speed of light divided by the wavelength. Therefore, the wavelength is going to equal Planck's constant times the speed of light divided by the energy of the photon. And that's what we figured out here above. Don't forget the amount the energy changed when the electron dropped from a higher energy level to a lower one is exactly equal to the energy the photon it gave off. And once you know the energy of the photon, then you can use this equation, Planck's constant times the speed of light divided by the energy of the photon will give you the wavelength. Okay? And I don't know if you want me to insert those values. We have Planck's constant is 6.626 times 10 to the minus 34 joule seconds. Okay. We know the speed of light is 2.9979 times 10 to the 8th meters per second. Okay. And then this is over the energy of the photon that we determined up here. Don't forget that this wavelength is going to be in meters because the speed of light is in meters per second. So your answer is going to be in meters. And it doesn't even say, it just says calculate the wavelength of the light. If all your answers are in nanometers, then you're going to have to take your answer in meters and change it to nanometers. Now, it was the chemist or physicist de Broglie that determined that, well, he reasoned that if electromagnetic radiation has both particle properties and wave properties, maybe matter also has wave properties and particle properties. And this is the concept, he came up with the equation for it. It's the de Broglie wavelength. And the de Broglie wavelength, you have an example problem in the chapter. I don't remember if it involves a tennis ball, but if you have things that have large mass, their de Broglie wavelength is so small that there's no equipment that could possibly measure it. So again, it's really more of a quantum mechanical thing. The de Broglie wavelength only makes sense for the smallest particles of matter, like protons and electrons and stuff. And also is measurable. Electrons have both particle and wave properties. Just like light, electrons can undergo diffraction patterns, which chemists or physicists thought that only light could do that. If you have a couple slits and you bombard it with electrons, on the other side of those slits you get cancellation and reinforcement, and it's really showing that electrons have wave properties as well as particle ones. Well, therefore, the de Broglie wavelength really lets you calculate what the wavelength of a small particle that has mass is. And it's just Planck's constant over the mass times, we're going to use u here for velocity, because the particles aren't going to be going the speed of light. They might be going pretty fast, but they're not going that fast necessarily. And it says here in an electron microscope, electrons are accelerated at great velocities. Calculate the wavelength of an electron traveling with a velocity of 4.3 times 10 to the third kilometers per second. The mass of the electron is 9.1 times 10 to the minus 28 grams. Now, one heads up here, when you're using this equation, because of the fact that you're going to be using joules and joule seconds for Planck's constant here, the mass has to be in kilograms. Now, if the problem gives you the mass in grams, you got to change it to kilograms. And also the velocity, and we're using u for velocity, it has to be in meters per second. And in this problem, just to make life miserable, the velocity is given in kilometers per second. So you got to convert the kilometers per second to meters per second, and you got to convert the mass of the electron from grams to kilograms. Okay? If you do it in one calculation, well, Planck's constant, 6.63 times 10 to the minus 34 joule seconds. And on the bottom we have our mass, 9.1 times 10 to the minus 28 grams, but we want to convert that to kilograms. 1 kilogram is the same thing as 10 to the third grams. Okay? Times the velocity is 4.3 times 10 to the third kilometers per second, but we want it to be in meters per second, so there's 10 to the third meters over 1 kilometer. This converts the kilometers to meters. This converts the grams to kilograms. And now it's set up. And your answer will be, a joule is the same thing as a kilogram meter squared second squared. So your answer will be in meters. No, I know the units are probably even more confusing than the problem, but here you have joules, the same thing as a kilogram meter squared per second squared times second here. And then you got a second on the bottom, 1 over a second on the bottom, so the seconds will cancel here and here, and you'll end up with meters squared over meters. So the wavelength will be in meters, trust me. Alrighty, well that's so much for practice from